Hello, all of you. Welcome to the 44th lecture on the course on analysis and modeling in chemical engineering. In this lecture, we will discuss some other examples of the application of graph theory in chemical engineering. We will look at how we can analyze reaction mechanisms using graphs. So, I will take an example of chemical reaction happening on a catalyst surface where, let us say, Z is the surface of a catalyst. So, clearly, as you know, that the reactants can come on what is known as the active sites on the catalyst surface. So, they can come and absorb there, and then they can do a reaction, and then they can basically go back after dissolving from the active site. This is the typical way a solid catalyst typically works. So, let us say here A and B are the reactants, and the chemical reaction is A plus B giving rise to AB, and it can be a reversible reaction in general. So, the first step is A gets absorbed on Z, and that I can represent as something like this: A plus Z giving rise to AZ, which I can call it as some kind of an intermediate species. And now this is basically, this is my AZ, and now this will AZ is going to react with the other reactant B, which is already in the gas phase. So, AZ plus B will give me something like A and B together on a catalyst site, that is my AB plus Z, but then AB will kind of leave and become a gas, right? So, what it is essentially saying is that AB is not remaining absorbed. As soon as AB is formed, basically it goes up, right? So, this kind of a thing is not happening. In principle, it may happen, but in this case, as soon as AZ comes in contact with B, that is A adsorbed on the catalyst interacts with B, B basically takes it away from the catalyst and forms the product AB, leaving aside the bare catalyst side, right? If you think about it in the overall scheme of things, this Z does not take a part in the reactor in the overall scheme. It basically is consumed in the first reaction but produced in the second reaction. So, basically the net production of Z in the entire chemical reaction including 1 and 2 is essentially 0. The overall reaction appears to be that there is no Z involvement, but Z instead is a part of this intermediate species at AZ, which is forming here. Now, if I, for example, want to develop a mechanism for this kind of a reaction, we can imagine that this intermediate AZ, and in fact also the active site Z itself, is basically some kind of nodes in my reaction scheme, and these nodes basically interact in order to basically give rise to the chemical reaction, and then eventually the products are formed and they go away, right? So, if we do that, in that case the active sites, which are Z, is also considered as an intermediate in some sense, or nodes of the graph, and the AZ, which is A adsorbed on D, is also considered a node. So, in that case I can represent the first and second reaction. In fact, we have 4 reactions because both reactions are reversible. The first reaction is basically the forward reaction of 1, which is A plus Z giving rise to AZ. That is my first reaction. Let me call it something like 1 plus to indicate that it is the forward reaction of reaction 1 listed here. So, in that reaction, A is coming in and reacting with Z to form AZ. So, essentially we can say that Z went from Z to AZ, the first arrow, Z went from Z to AZ involving a reactant A, which I am kind of not representing as a node, I am kind of representing as a curved arrow meeting this particular edge, just to indicate that it involved another reactant A. Now, The reverse reaction of 1 is AZ going back to A plus Z. And now you see again the same thing is happening. We are going from AZ to Z. So this is my 1 minus. And instead of A getting consumed in 1 plus, in 1 minus, A is getting released. So therefore, again I am showing a curved arrow for A now going out of the edge. Right. Soon I will not show this red edges here. They are curved edges indicating the movement of the reactants, but mainly we are interested in how the intermediates are behaving and how are they connected together, because they will decide the reaction mechanism which I am interested in. Similarly, for the second reaction, we have a forward reaction AZ plus B giving rise to AB plus Z, which is the forward reaction here going from AZ to Z. And then there is a reverse reaction 2 minus, which is AB plus Z giving rise to AZ plus B. So what this essentially represent, this graph represent all kinds of flow between the intermediates which are present in the system. In this case, we have two intermediates, Z and AZ. In the overall scheme of things, there is the net production of them is 0. But then while the reaction is happening, or in the mechanism of the reaction, there is a possibility of forming Z from AZ and AZ from Z. So this graph basically represent the interrelation between the two intermediates Z and AZ in the problem. How it is helpful? This can basically help us make a kinetic model for the chemical reaction, where now I am again looking at the two reactions and I see that at a steady state what is going to happen is that the net production of Z, the net production of active sites are going to be 0, and similarly the net production of the intermediates are also going to be 0 at a steady state, because in the end the final reaction does not contain Z or AZ. So net production of both of them are going to be 0. And now we have 4 reactions. So therefore we have essentially 4 rates. The first rate corresponds to the reaction Z plus A going to AZ. Let us say the rate constant for that is K1 plus, and assuming that it is an elementary reaction, the rate of consumption of Z is given as something like K1 plus Ca into the concentration of the active sites, which is represented by theta Z. It is some kind of a concentration of the active sites which are free for the adsorption of species A. Similarly, for the reverse reaction, we have AZ going to K1 minus Z plus A. So the formation of Z, this was from the 1 plus, formation of Z from the 1 minus is given as K1 minus theta Z, theta AZ. The number of, or the fraction of, or the concentration of the AZ intermediates in the problem, that is my theta, the coverage of the active sites by the AZ intermediate. So that means my first two terms, in the first reaction 1 plus it is getting consumed, second reaction Z is getting formed. Similarly, for the second reaction also we have a forward and a backward. The forward reaction gives me the formation of Z with some rate constant K2 plus. The rate for that is K2 plus Cb into theta Az, and the reverse reaction gives me the consumption of Z, and that gives me the last term here, right? So at a steady state, the net rate of production of Z is going to be 0. So therefore, the sum of this can go to 0. The same I can apply for the intermediate AZ in the problem. In the first reaction, the rate of production of AZ is given as K1 plus Ca into theta Z. In the second reaction, AZ is getting consumed and the rate of that is minus of K1 minus theta Az, the concentration of Az intermediate. Similarly, for the second reaction, for the forward reaction, Az gets consumed, so we have a minus term. And finally, for the backward reaction of second reaction, Az gets formed, so we have this, and that sum is also equal to 0. And finally, in my catalyst surface, either you have the Z sites or you have the AZ site. Let us say at the beginning of the reaction, the entire catalyst surface is bare, and we say that the net concentration or net fraction of the active sites is 1. Then if AZ is getting formed, then the sum of the concentration of Z and the concentration of AZ is equal to 1. We can interpret the concentration as fraction occupied, so that if I sum up the two concentrations, I will get it equal to 1. So if I now apply this idea, I can basically solve this equation and get theta Z and theta Az. But before we do that, we want to go one step further in the graph theory picture of this. What we will do is we will assign the weights to each of these edges that we have. So we have 4 edges corresponding to essentially 4 reaction, 2 for the forward and backward of first reaction and 2 for the forward and backward for the second reactions. I want to assign edges, all these edges with some weight, and that weight is basically whatever rate we have divided by the concentration of the intermediate, right? So for the first step, for example, the rate is K1 plus Ca theta Z. If I divide it by theta Z, we have K1 plus Ca. That quantity I will call the weight of the corresponding S, right? So basically, S weight is defined as the rate happening here by the concentration of the intermediate. So now we can write the net rate of the first reaction is the difference between the forward rate minus the backward rate. The forward rate for the first reaction is my K1 plus Ca theta Z, and the backward rate is minus K1 minus theta Az. So this quantity I am going to call as W1 plus, and this quantity I am going to call as W1 minus, right? So basically the term aside from the theta I am going to assign as the S weight, right? So then I can rewrite the net rate of the first reaction as the following, where I have also used the fact that theta Z plus theta Az is equal to 1, and net rate of the second reaction as something like this, right? And now at a steady state, clearly the net rate of the first reaction should be equal to the net rate of the second reaction. Why is that? Because we don't want Z or Az to get accumulated. So if Z is getting consumed here and Z is getting formed here, then in the overall scheme, the rate of the first reaction should be equal to the net rate of the second reaction. The net rate of first equation should be equal to net rate of second equation, because if it is not, then there is going to be an accumulation of Z and Az, which I don't want. So therefore, we are going to set R1 equal to R2 equal to R. And now we have an equation in terms of the S weights, which I can now solve, and we can get the expression of the theta Z and theta Az in terms of the edge weights in the graph. And we have 4 edge weights: W1 plus, W1 minus, W2 plus, and W2 minus. I can basically go ahead and solve for the rate R, and we can get an expression something like this in this particular case after arithmetic simplifications. And now we can see that we have everything in terms of basically the graph that is in the picture. So I'm assigning this edges, and from the edge weights given on the graph, I can find basically the rate of each of the steps that are taking place in the chemical reaction. Okay, so let us take one more example where we have slightly more complicated reaction, where we have essentially 3 intermediates. Here the AZ can transform into BZ. It is some kind of isomerization chemical reaction. So we have one extra step, AZ becoming BZ, and then BZ decomposes into B plus Z. Again, the net reaction is A going to B, essentially an isomerization reaction, but it is happening in 3 steps. First, A gets absorbed on an active site. In second step, this transforms into BZ. This was my AZ. Now we have BZ. And in third step, basically this BZ releases B and Z is remaining in there. Again, we can assign the weights for all the edges here, and we can do a graph. So from Z, for example, in the first reaction, the forward step is A plus Z to AZ, and I am calling this as something like rate constant K1 plus. So the rate here is given as something like K1 plus Ca theta Z, and then rate divided by theta Z becomes my weight W1 plus, and that is exactly what I have written here. So from Z I can go to AZ. From the same reaction, the backward step is AZ going to A plus Z, and that has a weight of W1 minus, which is K1 minus, right? Because the rate is K1 minus theta AZ. So this becomes now W1 minus, and I can extend this idea to basically all the 3 intermediates Z, AZ, and BZ, and we have a graph for this particular problem. Okay. Now, once we have this graph, we can also define something else in graph theory, which is known as a tree. Tree is a sequence of the graph edges which basically contains no cycles. As you can see here, in this case, we are forming cycles. Basically, Z and AZ itself forms a cyclical net of order 2, and same is true for AZ, BZ, same is true for Z and BZ, and in fact, the entire graph also is forming a cycle. But I can draw subgraphs of this graph which is not containing cycles. It's a subgraph of that graph that is not containing any cycle, and that becomes my tree. For example, Z to AZ is a subgraph. Subgraph meaning it contains some vertices and some edges from the original graph. So this is example of a tree. If there is no cycles, it forms a tree. Similarly, AZ to BZ is also a tree, and then I can also make trees containing all the vertices. From Z I can go to AZ, and then I can come from there to BZ, ignoring the reverse path because I don't want to form cycles. And what I form is again a tree that is called a spanning tree. So a spanning tree or maximum tree is a sequence of edges that contains, of course, no cycles for this to be called a tree, but joining all the nodes in the graph, right? And now we can go ahead and basically do all the spanning trees for this graph, and you will see like what exactly it gives rise to. But before that, there are some rules we have to follow, that the spanning tree should basically contain all the nodes in the graph, but we should ensure that we do not count two reactions starting from the same intermediate. Let us say something like this, where AZ goes to Z and AZ goes to BZ. It is a subgraph, but this is not called a spanning tree. Similarly, it should not contain cycles. So, two reactions of same step, both forward and backward reaction, that also will not be counted as a spanning tree, right? So, this basically represents therefore a sequence of transformations through which we can form a certain intermediate from other intermediates in the problem. So let's take an example here and we ask ourselves, how do we get Z? There are many possibilities. We can get Z starting from AZ, I form BZ and then form Z. The other possibility is I start from BZ, then form AZ and then form Z. And third possibility is I directly form Z from BZ. Fourth possibility is I get Z from AZ, right? So there are four different possibilities. One is like I start from the AZ and go there in 2 steps. Second is I start from BZ, go there in 2 steps, or I start from BZ and AZ and go there in 1 step, right? And all these spanning trees, the 4 in this case, in fact 3, the third one contains two in 1 step paths. All these spanning trees basically indicate how we can get to Z, right? So essentially, now since I have the weights corresponding to the chemical rate of reaction, I can basically sum over the weights of these spanning trees and they will get me the net rate of formation of any given intermediate in the problem, right? The same idea I can apply for node AZ. I can go to node AZ starting from BZ, then forming Z, then forming AZ, starting from Z, then forming BZ, then forming AZ, starting from Z and forming AZ in 1 step, starting from BZ and forming AZ in 1 step. And these numberings basically indicate the reaction number that we have. So we had 3 reactions, 1, 2, 3. Plus represents the forward reaction and minus represent the backward reaction. And now we can see that I can basically look at the net weight that we are getting from all these trees, right? How do we get a net weight? I basically multiply the edge weights which are forming this tree. So let's say here we have W plus 2 and W plus 3. So net weight is W2 plus W3 plus. Similarly here W1 minus W2 minus, and finally here W3 plus W1 minus. And since all the three that I was just looking at, they basically tell me how I can form Z. So therefore I can define a net weight of Z which is sum over the 3 weights listed here, WZ1, WZ2 and WZ3, and this gives me basically the net weight corresponding to formation of Z. Same thing I can do for AZ. Again, I have 3 spanning trees. I sum over the weights of this and I get something like this, and same for BZ, right? And then I can total this and it gives me the total weight of all the spanning trees which are present in the graph. How is it useful? If I have this, then basically let's say I am interested in theta z, it is actually given as simply wz by w, where wz I have figured by what we have done here, right? Now, this may look complicated. So, therefore, we go back to our earlier example and see whether this idea actually works or not, right? So, in the earlier example, I had only 2 nodes Z and AZ, and we can form essentially 4 spanning trees connecting Z and AZ. We cannot consider cycles, we cannot consider both forward and backward steps. So, there are 4 reactions which are taking us from Z to AZ, right? And there are two reactions forming Z. So I will basically add the weights for the two reactions. Similarly, for AZ, I have two reactions, so I can add the weight for the two reactions. By summing these two, I can get the total weight W. And now, using the formula I have described, I can get theta Z as WZ by W and theta AZ as WAZ by W. And we can go back and see that this is indeed the expression which I have obtained earlier, right? So therefore, we basically reduce a problem of reaction mechanism where we have to find the fraction of active sites or concentration of active sites to a problem in graph theory where by properly defining the is weights and things like that, we can basically write the problem purely from a graph theoretical standpoint, right? We can do the same thing for this new graph. So I have somewhat more complicated graph, but I already have computed the weights. So we can go ahead and find theta z, theta az, and theta bz for this particular graph, right? And I can now plug it in the equation for the rate. So now we have three reactions. So we have three net rates, R1, R2, R3, and at steady states, R1 should be equal to R2, should be equal to R3. The same logic which I had earlier, where I had R1 equal to R2 equal to R, right? In this example, because we have two nodes, but now in the new example, I have three nodes. So I have set R1 is equal to R2 is equal to R3 is equal to R. And then I can basically get the expression of R. And you see, quite interestingly, the form is quite simple as it stands, because I am the first term in numerator is simply a product of all the forward reaction is weights. The second term is simply a product of the backward reaction is weights divided by the total weight of the reaction. And this is a simple result we are getting from purely a graph theoretical kind of a framework. So this is how we can basically use graph theory for analysis of reaction mechanism. That is basically one other application of graph theory in chemical engineering, particularly if I am interested in catalysis problems. So with that, I conclude this lecture. Thank you so much.